this computer, and then I'm going to start sharing my screen. Okay, so this week I have four problems, and they're all, I guess I already told you that they're all shortest path problems. So let's get to the first one. So the first problem says that you have a microwave and it has a large number of buttons to quickly specify the time. The buttons are used for both adding time and for subtracting time. Okay, so, and then the microwave can run for at least 0 seconds and at most 1 hour. So 1 hour is 3,600 seconds. And the microwave will set the cooking time initially to 0 seconds. If a button press would result in a cooking time of more than 1 hour, oh sorry, I skip a line. If a button press would result in cooking time of less than 0, it will set it to 0. If it will result in more than 1 hour, it would set it to 1 hour. Initially, it's 0 seconds. There will always be a button adding at least 1 second to the cooking time. So now you have a set of buttons. You have to determine least amount of button presses required to set the microwave run for a certain amount of time. If it is not possible to enter the desired cooking time precisely, determine the smallest achievable cooking time above the target and the minimum number of button presses required for that cooking time. Instead, the microwave does not allow to adjust the cooking time once it started cooking. So let's keep reading. Okay. On the first line, there's one positive integer number, which is the number of test cases at most 100. Then you have two numbers, n and t. N is at most 16. It's the number of buttons available. And t, from 0 to 3,600, is the desired cooking time. And then one line with n space separate integers bi, which is the number of seconds added to the cooking time when button I is pressed. But this bi can be negative, so you can actually decrease the cooking time. Now, you might remember last week we had a problem that's the coin changing problem. So last week we have this problem where you have a set of coins and you want to find the smallest sum to pay, right? Because if you want to buy something that's $100, you might not be able to pay $100 exactly, but you can pay maybe 102. And then for that given sum, use the smallest number of coins. Okay, the last week there was this problem, and it's essentially the same problem except for one little detail. The little detail is that now your coins can be negative. Okay, and that's, well, there's one more detail is that when you decrease it to less than 0, then it's set to 0. If you increase it to more than 3,600, you set to 3,600. But that's these two details actually are not that important. So what am I trying to say? What I'm trying to say is that in fact, the coin changing solution that you had from last week can be used to basically solve this problem. Okay, how? So basically what you do is you say f, need a pen, f of n t to be the smallest number of button press using first n buttons. So of course at the beginning n is smaller, and to make exactly time t. And basically this would go from 0, 1 up to 16. These are the possible values, and these are the possible values are between 0 to 3,600 because those are all the times that you care about. And then you write recurrences the same way that we did. Okay, so you can go back to that presentation last week to see how the coin changing problem can be solved, and then this is exactly the same way. But I want to show you a different way of looking at the same problem. And quite often, dynamic programming can be modeled as a graph. Okay, so what is this graph? The graph, you need to figure out the nodes of vertices and then the edges. So what are the nodes? The nodes at the time 0, 1, 2, up to 3600. So there'll be 3601 nodes. And the edges will basically say that there's an edge from some node U to some node V. Okay. The weight of that edge will be 1 because it represents a button press. It's going to represent a button press. So what is V? V is going to be U plus the button, BI. Okay, so if, for example, U is 5 and there's a button, BI that's 7, then there'll be an edge from 5 to 12 because you can, in one button press, you can go from 5 to 12. Okay, does that make sense? There's a little bit of problem. So the little bit of problem is, what if BI is -7? So then if you try to do this, you might say 5 to -2, but of course you know that -2 doesn't exist. It's actually 0. If you try to go negative, it's 0. And likewise, if you go above 3600, you should go back to 3600. So basically what you do is you set up this graph with 3601 nodes. And in each position, in each node, you're going to have a bunch of edges. These are directed edges, okay? These are directed edges, so this is a directed graph. And it goes from U to U plus B1, U plus B2, and so on, all of them. And each of them have exactly the same weight. So you construct this graph. And once you construct this graph, then what you're asking is, what is the shortest path from node 0, because that's your starting point, you're starting at 0, to node T. That's where you want. And if there's no shortest path, then you want to know, if there's no way to get to node T, you want to know what is the shortest path to T plus 1, T plus 2, etc., until you have a node that you can reach. And the smallest one that works is the one that you want. Okay, so is there any question about how this graph is set up before I talk about how to solve this? Is it clear at all what is this graph and why this graph models the situation? Okay, so the important thing is that you're trying to model button presses, how many button presses, and if you want to convert it into the length of a path, in a graph, then each edge would have to represent exactly one button press. So a button press takes you from some starting place to some ending place, right? Takes you from a certain number of minutes to another number of minutes. And that's how I model this with this graph, where the nodes are the minutes. Now this graph is nice in that every single edge is exactly the same. So you can call it unweighted if you want. So there are no real weights to the graph, to the edges, because every edge is really the same thing. Or you can just say that every edge has the same weight. In any case, you can find shortest path of a graph with an unweighted graph with breadth first search. You can also use more sophisticated techniques at BFS. You can also use Dijkstra's if you want, but that's not needed. And if you remember your complexity from your algorithms class, if you have n nodes and m edges, breadth first search is n plus m, and Dijkstra is a little bit trickier. It's something like n plus m times log of n if you implement it right. Okay, so of course, breadth first search is better than Dijkstra. It's also easier to write. So basically, the problem involves two different steps. First, you have to build a graph, and then second part, you have to do the breadth first search. And I guess the third part is once you've done the breadth first search, you have to look at which one of these nodes is the smallest node bigger than or equal to t that has a path from 0. And typically with breadth first search or Dijkstra, you start from a node and you go to every other node. So you can actually compute the shortest path or the shortest distance from one node to everywhere else. So it's usually called a single source shortest path. You start from one place and then you go to every other place. Okay. So let me show you quickly my code. Okay, so here's my code. I will show you the main part, which is not very exciting. Main, I just read the number of cases, and then this basically loop the number of cases times, and then each time called solve. So solve just basically solves one single case. Okay, so what do? I read in n. I read in n and t, so I know the number of buttons, and I know the number of minutes that I'm trying to do. Then I am going to store, this is my the buttons, the n buttons. I'm just going to store this as an integer. And then this is the part where I start to do my breadth first search. Now I'm actually doing breadth first search and building the graph at the same time. So this is maybe a little bit more advanced. So you can do one of two things. You can build a graph, step 1. And then step 2, do BFS. So how do you do BFS? Well, what you do is you first have a queue, and then you have a queue dot push the start, in this case 0. And then while the queue is not empty, then what do? You get, let's call it, I call it current, is the front of the queue, and then pop it. So remember in C++, looking at the front does not remove the front, so you have to do it separately. And then basically for each neighbor of current in the graph, then you do something. If neighbor has not yet been visited, then queue.push the neighbor. Okay, there are some other things that I haven't in the code that I haven't talked about yet, but basically that's a basic structure of breadth first search. You push the starting node, and while the queue is not empty, you keep getting the front of the queue, and then for each neighbor of this current node, if you haven't visited, then you visit it by pushing the queue. Now, the key point is, how do you know which are the neighbors, right? If you already build a graph, I guess if you use a JSON to list, for example, then you just look it up. Use whatever graph structure. But when you build a graph structure, you have to do some computation to figure out who the neighbors are. So what I'm doing is basically, instead of building the graph first and then doing a BFS here, I'm actually doing that same computation right here to decide who my neighbors are. So let's look at the code. So first of all, I have this array D, which are from 0 to 3,600. And I'm going to set it to -1 to indicate that I have not visited it. So D is going to be the distance, the number of button presses from 0. -1 sets that I have not visited. So at the beginning, where I start, I can set the distance to 0, and then I can push it. While the queue is not empty, take the current node being the front of the queue, pop it, and now, okay, the indentation here does somehow is not working quite right, but I'm going to go through all my button presses for I from 0 to n. The next node is going to be the current node plus the button press. But then I have to do something here. The min 3600 just means that if the number is bigger than 3600, I make it 3600. And max 0 just means that if this number is negative, make it 0. So if you don't like this, you can write if statements. But basically, this just makes sure that if you're out of range, it's set it to 0 or 3600. And then here it says if the distance of this next node is less than 0, remember that we set it to -1 to indicate that it has not been visited. And if it has ever been visited, the distance will be at least 0. So if it's less than 0, it means that it's unvisited. Then what do? First, I remember that the distance of this next node, it's whatever the distance of the current node is plus 1, because I got here by pressing one more button from the current node. So however many button presses I need to get to the current node, I add one more. That's what I need to get to next, and then I push it. And this, it's all there is to it. This is the entire BFS from this. This is BFS here. It will compute the shortest distance to every reachable node. If you have a node that's not reachable, it will remain at -1. Okay, and when the queue is empty, it means that you have visited everything that you can possibly reach. Okay, so that's breadth first search. And then finally, the last part, I start my time at t. So I start my time at t, and now this for loop that seems a little bit funny. I set, actually, I don't know why I initialize here and initialize here again. But anyway, I initialize here, and then as long as the distance is less than 0, meaning that it's unreachable. As long as that time is unreachable, I increment. So I start at t, and then I go to t plus 1, t plus 2, and so on. As long as it's unreachable, I keep going, and when it stops, that's when it's reachable. So when it's reachable, I print out the number of key presses for that time, and also how many more seconds I need to press, or how many more seconds I need to cook. That's what the question asks. If you have to go t plus 2 instead of t, then you print 2, because you have to cook for 2 extra seconds. So that's a way to look at this as a graph problem. And anything else I want to say? There's not much more I want to say. Any questions? Is it all clear how this works? So I think all of you that are in 3620 have seen breadth first search. I don't know if you have actually tried to code anything like that, but here's breadth first search. Any questions? Okay, so the next problem, it's how do I, let's see here, what is the best way to do this? The best way to do this, I think, is to draw pictures. So let me draw pictures. Okay, so you have two shopping malls, and this is the top view of the mall. And they're going to give you some integer coordinates like this. I don't remember, clockwise, counterclockwise, doesn't really matter. But basically, they trace out the top view of this shopping mall. They give you these XY coordinates, by the way. So these are all the XY coordinates here. And then you have another shopping mall, and it's guaranteed that they do not touch each other. Okay, so here, let's say you have these two shopping malls. And the idea is that you are allowed, in one step, you're allowed to move up, down, left, and right. So the question is, if you want to walk from one mall to the other, what is the shortest distance? So for example, maybe you go this way, this way, this way, this way, this way. Maybe that's the shortest distance, I don't know. Or maybe you go the other way. So not only do you not know which way to go, you also don't know where you should start because there are many starting spots. You can start on any of these dots on the first mall, and you also don't know where you should end because you can end in any of those dots in the other mall. Okay? So that's the question. It's again a shortest path problem, but this time instead of saying you want to go from one spot, you can start from many different spots, and you can end at many different spots. So what to do? Anybody have any ideas? You have two issues: multiple source and multiple destinations. It doesn't matter whether you're trying to move from this mall to the other mall or vice versa because the movements are symmetric. So you can decide to move from this one to this one. Doesn't really matter which way you move. As long as you fix one of the building to be the starting point and the other one to be the ending point, is okay. But within this building, there are many starting spots, and within the ending points, within the destination building, there are many ending spots. Any ideas? Anybody has any suggestions on what to do? So the first thing I'm going to say is that the multiple destination is easy. In fact, you don't even have to do anything. What do I mean by that? Because usually most shortest path algorithm is single source, all destinations. It will automatically try to find the shortest path to every single destination anyway. So just like the microwave button problem that we just had, we basically computed all reachable places, the shortest distances, and then at the end, figure which one is best, which one is closest to the time that I want to hit. So here, if you want, you can just run breadth first search and the entire thing, and then after you know the shortest distance to everywhere, then you just look at the shortest distance for all these spots that the second building sits on, and then pick out the shortest distance. Okay, so that's one way. So in some way, you don't actually have to deal with this, but if you want, if you're using breadth first search, for example, the first time that you hit one of these, if you know that some of these locations are part of the second building, as soon as you hit any one of these, you can actually quit the breadth first search. You don't have to discover anything else because breadth first search always discover the things that are closest to you first. So if you want to make your algorithm more efficient, you don't actually look at all destinations. You want to say that as soon as you hit one of these destinations, you stop. Whichever one it is that you hit first, that's the one that you stop at. Okay, so but it's still relatively easy as long as you know at each location whether there's a building there, and if so, whether it belongs to building 1 or building 2, you can stop pretty much right away when you hit it. Okay, so basically then what happens is you need to have a distance array, but you also maybe need a label array that tells you if a point is building 1, building 2, or no buildings. It could be just a point that is in space and there's no building in between. So you can have an array that stores at each location whether you are part of building 1, part of building 2, or nothing. Okay, so multiple destination is not too bad. Turns out that multiple start points, it's also really easy. So how does breadth first search goes? You say, okay, the distance of the start, it's 0, and then q dot push start, and then you have while not q empty do a bunch of stuff. Okay, this is the basic structure of BFS. Here, we're pushing the start, the first node. The start, which has distance 0. Actually, here, instead of pushing a start, you can actually just, for all v on building 1 boundary, just push v and set the distance to 0. So instead of pushing just one single node in your breadth first search that has distance 0, we realize that any of these spots, if you start any of these spots, it's distance 0. All of these spots, if you start them, is distance 0. All of them. So what do? All you do is you push them all into the queue and set them to distance 0. Then run breadth first search the way that you normally run it. And then this multiple source is automatically taken care of. So the same trick you can use with Dijkstra's algorithm as well. If you have a graph where the edge weights are not the same, if it's not always the same weight, you can use the same trick. If you have multiple starting points in Dijkstra's algorithm, you can just as easily push all of the starting points at the beginning of the Dijkstra's algorithm, and then run Dijkstra. And for those of you that may remember, Dijkstra's and breadth first search are almost the same, except that in Dijkstra you use a priority queue instead of a queue, and then you have to update your distances a little bit more than just saying whether a node has been visited or not. But otherwise, breadth first search and Dijkstra are very similar, and so many of the tricks that you can use for one, you can use for the other. So now, do I want to show you my code? Now, the code that I show, unfortunately, or fortunately, this is a little bit strange. You see that I have a queue that I maintain myself, and I have a queue with, I try to use an array to store the queue, and I have a head pointer and a tail pointer that I keep track of where the head and tail is. Believe it or not, this problem was a contest from 2006, and it's prehistoric when it comes to the STL. I wrote this code before STL was even really widely in use. So all of that stuff that I do here, you don't really have to do much. You just use a queue now. You don't need to do your own queue. But basically, what am I doing? At the beginning, I set everything to be not visited. So visited is just a Boolean array. The problem says that all the coordinates are between 0 and 2000. That's why I can do this. I have this loop that sets everything from 0 to 2000 to be not visited. Then the first polygon, the first mall that they give me, I keep reading the X and Y coordinates, and I push it under the queue. So I push all of them to the queue. And here, the visited, I set them to be 1 to indicate that I visited and they are the first building. And then second building, I kind of cheated and I set the visited to be 2. I haven't officially visited them yet, but this is basically my label. So my label is either 0 if it's nothing, 1 if it's first building, and 2 if it's second building. But as I start exploring anything that's visited, it will be set to 1. And then this is basically my horrible way of writing my own queue to say that this is, well, it's not empty. If basically take the head of the queue, then this basically says, look at all my neighbors. Um, if the neighbor is actually building 2, then I'm done. I found it. So it's whatever my distance is plus 1 more step. And I set done equals to 1, so I quit here right away. And then otherwise, if it's not visited, then I push it in the queue. So if I was writing this in a more modern C++ with STLQ, this would be easily half the size. I mean, you saw my previous preferred search code from the other problem. This is basically exactly the same. The only problem is that at the beginning I got to insert all of building 1 into the queue. Another thing that I do, this is something that I often do. So forget about this shorts and long business. Short is just an integer that's 16-bit. For some reason, I decided to use the short. Don't ask me why, but back in 2006, maybe that was important. Now, one of the things that I do is, if this is x and y, I need to know who my 4 neighbors are, right? So my 4 neighbors, this would be x, y minus 1. Well, I guess this is y plus 1. This would be x, y minus 1. This is x plus 1 and y, and x minus 1 and y. So if I'm here, I need to figure out who my 4 neighbors are. How do I do this? So one of the ways that I like to do things is I represent for any position, how do I get to my 4 neighbors? Well, this is basically adding a vector of 0, 1. This is adding a vector of 1, 0, 0, minus 1, and minus 1, 0. So if I put them, the 4 together, then I basically have a delta x and delta y. I have a minus 1 and 0, this one. I have a 1 and 0, this one. I have 0 and 1, and 0 and minus 1. So I put that into this array, these 2 arrays. One is the delta x and one is delta y. And as I loop through the 4 positions, 0, 1, 2, 3, then the value of dx and dy will give me the neighbor. So here I loop through the 4 directions in my neighbors, and then x plus dxi and y plus dyi will basically loop through these 4 neighbors. Now I did not actually position these 4 directions in any particular way. I could have easily ordered them in different way, but the way that I've done it now, basically it just says, look at the left neighbor, then look at the right, then look at the up, then look at the down neighbors. There's another common way that I like sometimes. I would, the 4 directions, again, I still have 4 directions, but this time I would call maybe this one 0, this one 0, 1, 2, and 3. So instead of in this order, I would go up, right, down, and then left. So why do I do this? Because if I do a clockwise turn, that's the same thing as taking the direction plus 1 mod 4. Oh, hang on. Let me try to press the mute button on my family members. Oh, yeah, leave it. Okay. And then if I do counterclockwise, if I want to turn counterclockwise, whatever direction I'm turning, then I'm basically subtracting by 1. But subtracting by 1 is the same thing as adding 3. Okay, so adding 3 and subtracting 1, it's the same. So this is the clockwise turn, and this is the counterclockwise turn. And that makes it easier if I'm modeling a situation where I also have to worry about which way I'm turning to get to the next direction. Okay, now pop quiz, I guess. So if this is 0, 1, 2, 3, then whatever direction I'm in, if I want to do a clockwise turn, then I do d plus 1 mod 4. If I want to do counterclockwise turn, then one of the things that you might say is I take d minus 1 mod 4. So for example, 3, if you want to turn counterclockwise, 3 minus 1 is 2, 2 minus 1 is 1, 1 minus 1 is 0, 0 minus 1 is, okay, so 0. If d is equal to 0, then d minus 1 mod 4 is negative 1 mod 4, which is what? What are you going to get? Anybody knows? Anybody willing to say anything? Oops. Okay. Somebody unmuted. Who unmuted? Blake, you want to say something?
No, not necessarily.
Okay. All right. So let's look at the simpler case, d plus 1 mod 4. So if you're 0, you turn this way. 0 plus 1 mod 4 is 1. 1 plus 1 mod 4 is 2. 2 plus 1 is 3. 3 plus 1 is 4, but 4 mod 4 is 0. So everything works. Minus 1 mod 4, what you want, it's 3. Because when you do 0 minus 1 mod 4, you want to get it to 3. But are you going to get 3? And my answer is
No.
I don't know. Because in the C++ standards, whenever you try to take the divisor, when you divide a number, integer division, where one of the two or both are negative, then the C++ standard says that there are basically two answers that you can get. You can get 3 or you can get minus 1. Either one is acceptable, and it depends on your compiler, your operating system, your CPU, and what they call implementation dependent. The only thing that C++ guarantees is that if you have A and B, assuming B is not negative, of course, B is not 0. If you have quotient and the remainder, the only thing it guarantees is that A has to be the same as B times Q plus R, and the absolute value of R has to be greater than or equal to 0 and less than the absolute value of B. And what that means is that the remainder can be either positive or negative. That's allowed. Either one is allowed. And the quotient that goes along with it also means that if you choose the remainder to be positive, it gives you one quotient. If you choose the remainder to be negative, it gives you another quotient. And both sets, as long as the quotient and remainder are consistent by this relationship, both possible sets of answers are legal, C++. So what am I trying to say? What I'm saying is, do not do this, because this is not safe. You don't know what you're going to get. If you're lucky, it doesn't work on your machine. If you're not lucky, it works on your machine, but then someday when you run your code on another machine, it doesn't work. Okay? So what is safe? What is safe is to realize that if you want to go counterclockwise 1 step, it's the same thing as going clockwise 3 steps, right? So if you have a clock, right? If you have a clock, right, this is 12 and this is 1, 2, and so on. You want to turn this way by 1 step. That's the same thing as going this way 11 steps. You wouldn't know the difference. So the idea is that you add 3 instead, and then you don't have to worry about ever going into negatives. All right, so this is a little aside, but it's a very important thing because a lot of times people don't pay attention, and then they don't know that this is a problem, and then they get, of course, trapped, and then they spend forever trying to figure out their bug because on the machine they cannot reproduce the bug. Okay. Next problem, this flowery trail. So what is the problem? The problem is you have a map. Okay, you have an entrance here. This is where you want to go. This is where you start. The highest peak, this is where you want to go. Okay, so you always start at 0 and you always end at the node with the largest node number. Each node, so each edge, so between nodes there might be some edges. Okay, so there are, these edges means that you can go both ways from 2 to 7 and 7 to 2, and the length of that edge 600, 510, and so on. Okay, so that's the first part of the setup. What you want to do, why are some of these yellow? You want to go from 0 to 9 using the shortest path. So here, for example, this path, here, then here, then here, it's 920. 100 plus 200 plus 620, the length is 920. It turns out that this is the shortest path, but shortest path does not have to be unique. There may be other ways to get to the same spot with 920. So if you go this way, that would also be 580 plus 90 is 670, plus 250 is also 920. And because both of these are 90, you can also take this way, like this. So there can be many shortest paths. And this problem basically says that you want to identify all the edges that is involved in any shortest path from 0 to 9, or from 0 to the highest node. Okay, so for example, this edge is not involved in any shortest path, so you don't select it. This edge is not involved in any shortest path, so you don't select it. But this edge is involved. This edge is involved in some shortest path, so you want to select it. And basically, if you read the problem carefully, you have to add up the lengths of all the edges that are selected, and then multiply by 2. Okay, because for some reason you want to put flowers on both sides of the road, so you have to multiply by 2 to say that there are 2 sides of this road. But anyway, the main thing is that you want to have a shortest path. Actually, maybe you don't care about the shortest path, but shortest path from 0 to 9, but all the shortest path, because there can be many of them. And then you want to identify all edges belonging to some shortest path. Okay, it doesn't, so there's, for example, this edge, it's involved only in one shortest path. This edge is involved in 2 shortest paths, but we count them the same way. It's only one, we only count it once. Right, this edge is included in this shortest path and also this shortest path. So we want to figure out for each edge, is it part of a shortest path or not? Okay. So this is a weighted graph. It's an undirected graph. So it's undirected, weighted. You also only want a single source, and I suppose single destination, but maybe you don't care about that because some single source is what most algorithms will give you anyway, and multiple destinations. So this is classic Dijkstra's algorithm. As long as, and you have to remember, Dijkstra's algorithm only works as long as these are weighted and all of them are non-negative. If you have any negative edges, Dijkstra's will not work. I don't know if you talk about that, but anyway, the problem here only have non-negative edges. Okay, so let's look at the input section. Okay, so also it is guaranteed that for the given inputs, there's some path from the park entrance to the highest peak. So you don't have to worry about the first part finding any shortest path is not solvable because there are no paths to get there. Okay, so P is the number of points of interest, so that's the number of nodes. T is the number of trails, that's the number of edges. Nodes points are identified from 0 to P minus 1. Entrance point is 0. Highest peak is P minus 1. So those are, this 0 is the start, P minus 1 is the destination. Then you have a bunch of T lines containing characterized trails, each containing P1 and P2 and L, meaning that P1 and P2 links what the edges link. Now you have to read this maybe carefully. P1 and P2 are not necessarily distinct. That means that you could have a loop that links a node to itself. Usually those you can just ignore, but it actually doesn't matter. You can put it in any way into Dijkstra, it will just ignore them anyway. And the edge will have length L. Okay. How many nodes can there be? 10,000, up to 10,000, up to 250,000 edges. Each length is at most 1,000. So if you have this many nodes, okay, this many nodes, each length of each edge is at most this, then each path, the total path, the cost can be at most 10,000 times 1,000, which is 10 to the 4, 10 to the 3, so 10 to the 7, which is well within 32-bit integer. Also, Dijkstra's complexity, it's n plus m times log n. So n plus m here, n is 10,000, m is 250,000. 250,000 is what matters. And then log n is not very big. So this is well within the range of what Dijkstra's can do. Dijkstra's can easily handle something with 1 million nodes and about 1 million and so edges. So that's not an issue at all. But Dijkstra can only tell you the shortest path from one place to another. Okay, it doesn't tell you what edges are used in the shortest path, especially if there are multiple shortest paths, right? So you can't just say, call Dijkstra, find the shortest path and call it a day, because Dijkstra will only give you one shortest path. You need to know all the shortest path. So you have node 0, you have node P minus 1, and then you have something in between. You have a cloud of edges and nodes. So the question is for each node, so if you have, let's say, and let me draw this better. If you have a node here, U, and a node B, and there's an edge between them of length L, is this part of any shortest path from 0 to P minus 1? Is there a way you can go from here to U, then to V, then to P minus 1? So that is the shortest path. If there is, then this edge should be included, otherwise it should not. So it's this edge in some shortest path from 0 to P minus 1. That's the question. What to do? So let's imagine that you need to, so what if I want a path? What if I want a path from 0 to P minus 1, but I must use this edge. Okay, so I want a path from 0 to p minus 1, but I must use this edge. What is the shortest path there with this restriction? Okay, so let's think about that. Now we may notice that I draw the arrow u to v. Okay, so here this edge is undirected, but I'm saying, what if I must go from u to v? So I will have to ask the same question going the other way. If you have this edge, I have to ask this question twice. So what if I'm forced to use u to v? Well, then to go from 0 to p minus 1, I must take a path from 0 to u. Then I must take the edge from u to v, and then I must take a path from v to p minus 1. Okay, that's how I can go from 0 to p minus 1 if I'm forced to use this edge in the middle. Now, the edge in the middle, of course, the cost of the edge in the middle is L. That's given. But what about the path from 0 to u? Well, I actually don't care what path I take. Any path will do. But because I want the shortest path overall, I want the shortest path from 0 to u. And similarly, if I want to go from v to p minus 1, I want to take the shortest way to get there, because I don't really care what edges I use anymore. I just want to get there as quickly as possible. So the distance from 0 to u, so d being the shortest distance, plus L plus the distance from v to p minus 1, it's going to be the cost of this path, assuming that u to v must be used. So if you add that up and the cost is exactly the same as the shortest path from 0 to p minus 1 with no restriction. So remember that let's imagine that we already computed the distance from 0 to p minus 1 using Dijkstra with no restrictions on what edges you can use. And if you add the restriction that you must use this edge, the cost is the same. That means that this edge is part of some shortest path. So let me say that again. If you restrict your shortest path to use a particular edge in this direction, then the best cost you can ever achieve is this. You cannot do any better if you're forced to use the edge from u to v. You must go from 0 to u, then take that edge from u to v, then go to p minus 1. And if doing that actually gives you the best cost, then this edge must be part of some shortest path. It might not be the only shortest path, but it will be part of some shortest path. So if you follow that logic, then what you have to do is that for each edge, you have to check. For each edge, if you decide to go u to v, you check this. If these three things added together is the same as the distance from 0 to p minus 1. But you also have to check from v to u as well, because you can take this edge either from u to v or v to u. So you have to check both ways. In any case, if this equality holds, then this edge must be part of some shortest path from 0 to p minus 1. Okay, I'm going to stop and take a short break for people to catch up if you have questions. Any questions about why that is? Yeah, actually, I'm just going to erase everything. So for each edge, u to v, and I have to remember that this edge, I have to check both u to v and v to u of what length. L if what? The distance from 0 to U plus the length L, which goes from U to V, plus the distance from V to P minus 1, it's exactly the same as the distance from 0 to P minus 1, then this edge is chosen. Meaning that this edge is part of some shortest path from 0 to P minus 1. So that's the main algorithm. And then the question is, how do you compute all of these? So D0 anything. So if you want to know what is the distance from 0 to everywhere, right? You need to know from 0 to U, 0 to P minus 1, and this 0 to U will be needed for all the different, or many different U's. Well, you run Dijkstra starting at 0. That will compute the distance to all of the other nodes. But this one is a little bit different. This one is D of something to P minus 1. The second part is always P minus 1, but the first one can be anything. Okay, because you try it for all the edges. Well, because this graph is undirected, the distance from anywhere to P minus 1 is the same thing as distance from P minus 1 to everywhere else. So you can actually run Dijkstra starting at the ending point and get the distance from basically from everywhere to the destination. And if you compute basically compute Dijkstras twice, one at the start, one at the end, working backwards, and then for each edge you just check this equality, and then you can basically get the answer. So let me give you a quick glance of my code. So the first part, there's Dijkstra's algorithm. What should I say? Dijkstra's algorithm is in my code library, so you should go and check it out. But basically, you have a graph structure that's adjacency list. There's a constructor that starts with how many nodes you have, and then you have these methods that add an edge between U and V, from U to V, with this weight, and this add edge right now actually it adds it both ways. Okay, this particular version I believe is actually our World Finals library, but it doesn't matter whether you use the World Finals library or the normal code library. If you go to the code library, there's a version of Dijkstra sparse for sparse graph, and this is the code. Anyway, I'm not going to go through how you write Dijkstra. So what do? You create a graph with P nodes. For every edge that they give you, you read in the 2 vertices and the length, and then you call add edge. Then I run Dijkstra from 0 and run Dijkstra from P minus 1. And these two matrices, D1 and D2, stores the distances from 0. D1 stores the distance from 0 to everywhere else. D2 store the distance from P minus 1 to everywhere else. P1 and P2 are 2 auxiliary arrays that you can use to get the actual shortest path if you just want any shortest path. But basically for this problem, it's not used. And if you actually read the code in the code library, it explains to you how do you get the paths from P1 and P2. Anyway, so the distance from 0 to P minus 1 is just D1 to P minus 1. Okay, D1 is from 0 to everywhere else. To where? To P minus 1. And then sum, it's basically the sum of all the chosen edges. So what do? I go through all the edges. So this basically go through every node. For each node, look at the adjacency list for that node. And so this edge, so this E basically goes from I to E dot 2. So this is my U and this is my V. In my data structure, I have different labeling, but I'm at node I, it goes to here. So I is actually my U and V is actually this E dot 2. So if the distance from 0 to U is negative, negative means unreachable. So if you cannot get from 0 to here, or you cannot go from V to P minus 1, if both of these are, if either of these are unreachable, I ignore that edge. There's no reason to even look at it. Otherwise, if the distance D1I is this one, so this is D1I, and this is D2 E dot 2, and then E dot weight is L. If you add these three things together and it's exactly the same as the best distance from 0 to P minus 1, then I select this edge by adding it to the total running sum. Otherwise, I don't. So anyway, the main thing is that if you have Dijkstra's algorithm already, it is fairly straightforward to code once you realize what you need to check. Of course, when I say straightforward, I mean that assuming that you're familiar with how I set up a graph with the data structure and how I call Dijkstra's and so on. If you've never seen this code before, then it's a little bit tricky. But basically, the graph data structure is just a vector of edges, and edge is just has two things, which node it goes to and the weight of that edge. So it's basically the adjacency list representation. So each node would have its own vector, and each vector would have two fields. First field would be where it's going to and the weight of that edge. So every edge will have where it's going to and the weight of that edge, and so on. Okay, so what I do in the code to go through all those edges is just for each I, for each node, okay, so for each node here, look at the neighbors, this list, G dot neighbor I is this vector. I go through it with a for loop that loops through all the elements E. In each element E has two parts, E dot weight and E dot 2. So each element is an edge, where it's going to and what's the weight of that edge. Okay, any questions? All right. The last problem, it's a problem that looks fairly straightforward from the start, and actually this one was the one that caused me a lot of grief. You can see, okay, compile error you can ignore because I was trying to fix something without even compiling. And anyway, I got 3 wrong answers before I got one that's right. But I can't tell you what the issue is later. Okay, so what is the problem? This problem doesn't really even have a story. It's just a textbook problem, it looks like. So you start with N, M, and Q. N is the number of nodes, 150 up to 150. M is the number of edges, which is between 0 and 5,000. And then Q, which is up to 1,000, is the number of queries. Those are numbers 0 to n minus 1. Then there are M lines, each line consistent with 3 integers, U, V, and W, indicated that there's an edge from U to V. So this is, when you see this, from U to V, that's a directed edge. And the weight, it's between minus 1,000 and 1,000. Okay, so now, as soon as you see this, if the weight can be negative, you have to know that Dijkstra cannot work. You cannot use Dijkstra. And then follow Q lines of queries, each consisting of 2 two node numbers u and v, asking for the minimum distance from u to v. And then at the end, input will be a line containing, input will be terminated by a line containing 0, 0, 0. For each query, output single line containing the minimum distance from u to v, or the word impossible if there's no such path from u to v. So far, still pretty normal. But then, this is a part that's a little bit strange. You can also write, you can also answer minus infinity, negative infinity, if they're arbitrarily short paths from u to v. What the heck does it even mean? Okay, so how can you have an arbitrarily short path? In other words, there's no shortest path. And this is something that is only possible when you have negative weights. If you don't have negative weights, this is not possible. So what is the situation where you can have no shortest path? Now, for those of you that are in 3620, I think I remember hearing you guys talking about Bellman-Ford. Is that true?
Yeah, we talked about it in that class as well as my networking class.
Okay, so you might have seen this already. So anyway, the reason why you can sometimes not have a shortest path is, for example, you can have 1 to 2. Let's say you have cos 1 to 3, and then maybe you have 4, and then maybe this is minus 10 and minus 10. So if I ask you what is the shortest path from 1 to 3, well, you go from 1 to 2, and then normal people would say, oh, 1 to 2, 2 to 3. So the answer is 2. But the problem is, if you go from 1 to 2, go to 4 and go to 2, right? 1, then 2 to 4, back to 2, and then to 3. That's shorter because you managed to subtract 20 by taking a round trip from 2 to 4 and back. But there's nothing that stops you from going on that round trip over and over and over again. And every time you go over that round trip again, you're going to decrease the cost. So there's no shortest path, because whatever answer you give me, I can give you something that's 20 less by taking another round trip from 2 to 4. So basically what you're looking for are negative cycles. If you have negative cycles, then you have to be careful. But it's not all negative cycles that you have to worry about. You have to worry about reachable negative cycles. What do I mean by that? Okay, so if I ask you, what is the shortest path from 1 to 5? The answer is 10, the shortest distance. Even though there's a negative cycle over here, it doesn't affect this result because it's not reachable. So what do I mean by reachable? It means that you can, if I'm looking for a shortest path from u to v, and there's a negative cycle that involves the node w, then I must be able to go from u to w and w to v. If I cannot go from u to w, or if I cannot go from w to v, then this negative cycle does not affect my answer from u to v. Okay? So that's the first thing. And the other thing is that I am basically going to be asked for between any starting point and any ending point. So this is what is called the all pair shortest path problem. I want to know the shortest distance, in this case just distance, the shortest distance from any node to any other node. And there's a very, very easy to write n-cubed algorithm. And it's called a Floyd-Walsall algorithm. Did you guys talk about that in 3620?
Just mentioned it today as what we're going to talk about on Thursday.
Oh, okay, so this is right on time. Okay, so Floyd-Walsall algorithm. What's the setup? So first we have an array Dij to be initialized. Initially, the distance from I to j. Okay, this seems a little bit strange because we're y distance. We don't want distance. The edge weight. So if you have an edge from I to j with a certain weight, you put that weight in there. What if there's no edge? If there's no edge from I to j, you put infinity. And I'm going to put infinity in quotes because I guess there's no good proper infinity, but basically a big number. Okay, so we'll just say infinity for now. We'll pretend all the mathematical definition of infinity that we have. Anyway, so this is initially. The algorithm goes like, at the end of the algorithm, dij would be the shortest distance from I to j. Infinity if I to j is unreachable. So if you cannot go from I to j, then it's still going to be infinity. Okay, now, one thing that's it's common, set dii to 0. This is common. Okay, so when you have a node going to itself, the cost is 0. So the initial step usually sets the diagonal entry to 0. Okay, so I promise that this is a really easy to write code. Here it is. For k is equal to 3, k less than n, k plus plus. For I is equal to 0, I less than n, I plus plus. For j equals 0, j less than n, j plus plus. D of ij, it's equals to the minimum of dij and dik plus dkj. That is the end of the algorithm. 4 lines. This is one of the most, I guess you can say, in terms of the length of the algorithm, this is probably the shortest piece of code that is useful. That's very useful. And clearly, this is n cubed time because you have basically 3 nested loops. Each has n iterations. And inside the loop, you do a simple calculation. So intuitively, what you can see is that in order to go from I to j, it's saying, well, you can go from I somehow to some intermediate k, and then somehow to j. Or you can just ignore k and just go without using k. So if you go without using k, it's dij. If you go with k, then you go take a path from I to k and k to j, k plus from then k to j, add them together. And you have this loop that basically incrementally allow you to use more and more nodes as intermediates, and then at the end, you're allowing every node to be used as an intermediate, so you're basically allowing all paths. There's a lot of very intricate detail in, why can you do this with only one array and not have to copy things back and forth? Why do you not have to worry about overwriting results and all that before you finish using it and so on? So the proof is actually not so easy, but the writing of the algorithm is very easy. So if you just run this code, at the end, dij will be the shortest distance, and then you're basically done. Why? Because if they ask you what is the distance from u to v, you just read this, you just read duv, and then you have basically, you might have a single number, or it may be infinity. Infinity means it's unreachable. But there's a problem. The problem is, what about negative cycles? Okay. How do you deal with negative cycles? How do you even know there's a negative cycle? So a negative cycle is detected, negative cycle involving V. So if you have a negative cycle that involves the vertex V, then dVV would be less than 0. So if you look at the diagonal entry in this matrix and it's negative, that means that there's a negative cycle that start at V, somehow go a long way, and then come back at V, and the whole thing is negative. Okay, so maybe I should use W since we have U and V in the other. So what if I ask you, what is the shortest distance from U to V? You have a few situations. It could be that DUV is infinity. That's the easy case. It's unreachable. You're done. You cannot go from U to V. If it's not infinity, then you have to say, okay, check all W such that D of W is less than 0. Okay, so if you have no such W, then you have no negative cycles anyway. But if you do have this W, that means you have a negative cycles. If DUW is not infinity and DWV is not infinity, what that means is that you can go from U somehow to W, somehow to V, and during this W, you can go negative as many times as you want. So if that's the case, if you ever find a situation where you have a W that has part of a negative cycle and it's reachable from U and V is reachable with that W, then you write negative infinity. That's your answer. If after you check all of these things and nothing tells you that your answer is negative infinity, then just output D of U V, because you're not part of any negative cycle. So Bellman-Ford is also n-cube time, but it's a little bit tricky. It's different because it will only work from a single source. But this is n-cube time, but it will get all pairs. So why is Bellman-Ford better? Right. So okay, let's look at this. So Floyd, it's bigger of n-cubed, and it will work. Basically, it will work to get you the distance between anything. So all pair, shortest path. Bellman-Ford, you will only do single source. So it's not all pairs, it's just one single source to any destination. And the complexity, what do you guys say the complexity is in your class? Do you remember? Anybody?
Isn't Bellman-Ford also n-cubed?
Yeah, okay. So I guess I want to ask the people that are taking 3620 what you say about the complexity, if you remember. So is it n-cubed? It can be. So most people, when you actually look at the actual implementation, is n times m, where n is the number of nodes and m is the number of edges. So if you have a dense graph where m is about n squared, then yeah, it's basically n-cubed. Or if you use adjacency matrix, that's also n-cubed. If you use adjacency list and your graph is not so dense, then it's smaller than n cubed. So yeah, if it's also n-cubed, then you might be asking, why do you use Bellman-Ford when Floyd used the same computation but gives you all the pairs instead of just one single source? But the reason is that Bellman-Ford can be faster than n cubed if you don't have a dense graph. So that's the reason why it's fast. Why you might sometimes want to use Bellman-Ford even though it seems to be less powerful because it can be faster if you don't have a dense graph. If you have a dense graph, then I guess it doesn't actually matter. It's always n cubed. Okay, so I guess maybe I'm not going to show you the code, but why did I have so many incorrect submissions? So one of the things that maybe it's not so clear, and they are intentionally not so clear, is that they tell you that there are m lines, each indicating that there is an edge, UVW from U to V with edge W. In nowhere do they say that U is not equal to V. So U and V can be the same, and then you have a node, and this edge weight can in fact be negative. So if you, and in fact they can give you multiple edges, so one with minus 10 and one with minus 100 and so on, and then you have to remember take the smallest one. So you have to remember that even though they give you an input, you don't just store it in there, you have to compare with what's already in there and take the minimum. And one of my issue was I always set the self loop to be 0, which of course is wrong if they give you minus 10. Similarly, they also never tell you that there cannot be multiple edges with different weights. And in that case, you have to make sure that you keep the one that's smallest. So those are I guess those are the two things that trip me up a little bit, even though I had the algorithm more or less correct. Okay, so anyway, I think those are all the problems that I picked this week. They are in some way very standard exercise of shortest paths. I chose something that used DFS. I chose something that used Dijkstra. I chose something that used Floyd's. But they are also not completely straightforward. All of them have a little bit of a twist. You have to do something a little bit more than just computing the shortest distance. So hopefully that if you can, look at the code, it's in my GitHub. All my solutions on Caddis on my GitHub repository, so you can look at how I do things. And yeah, if you have any questions about how things are implemented, feel free to ask me. And for those of you that are taking 3620, hopefully that will help you a bit understanding some of these topics further. Let me stop the